Okay, colligative properties of strong electrolytes. We said that strong electrolytes affect these colligative properties more than non-electrolytes because they break into more particles, right? But they don't always behave exactly like we would expect them to. And so we need a correction factor in here, and that's called the Van 't Hoff factor. It's given the symbol I, and it's the ratio of moles of particles to the moles of formula units dissolved. So it's the moles of particles that are actually in the solution divided by the moles of formula units dissolved. These are not always exactly what we expect due to ion pairing. So this is ion pairing. Here, the sodium chloride dissolves completely. This is an unsaturated solution. There's no sodium chloride crystals down here. But this solvated chloride ion and this solvated sodium ion effectively pair up. They're just hanging out together. And because they're hanging out together, then they act like one particle in terms of colligative properties. So what we see for sodium chloride is we expect that the Van 't Hoff factor would be 2. Because if you take 1 mole of sodium chloride, you get 2 moles of ions, right? So you expect 2 moles of ions, 2 moles of particles for 1 mole of formula units dissolved. But it's actually 1.9. And so we see that the actual Van 't Hoff factors are a little lower than what we would expect. And it's not just a constant percentage or anything here. Magnesium sulfate is much lower, while sodium chloride is only a little bit lower. And so if you're doing precise work, you have to include the Van 't Hoff factor. And these are just measured experimentally. There's not really a theoretical equation behind it. And again, these things do not need to be memorized. If you're not given the Van 't Hoff factor or not given access to the tables, then you would just go ahead and use the expected value because you do have to consider the number of particles. So this is what we have is we need to use the Van 't Hoff factor in each of these equations to correct for this ion pairing. And so you just multiply by this factor. So let's do a question. Calculate the freezing point of an aqueous 0.1 molal iron 3 chloride solution using a Van 't Hoff factor of 3.2. So they gave us the Van 't Hoff factor. So the Van 't Hoff factor equals 3.2. What's the equation we're going to use?
The TF equals molality times the KF, which is like the infinite chart.
Yeah. So delta TF, the change in the freezing point, is the molality times the freezing point depression constant. And now that we know about it, we're going to stick the I in here. Yeah.
Oh, and we're using that freezing point 1 because it says freezing point in the equation, right?
Yes. So I happen to remember that the KF for water was 1.86 degrees Celsius per molal. So we don't have to go look that up. So the freezing point depression then is going to be 3.2 molal. I'm sorry, that's not molal. There's no unit on the Van 't Hoff factor. Times the molality, 0.10 molal, times the freezing point depression constant, 1.86 degrees Celsius per molal. So molals cancel out. We have 3.2 times 0.1 times 1.86. We should have 2 significant figures here, so this is going to be 0.60 degrees Celsius.
Why is it 2, not 3?
The Van 't Hoff factor is just 2.
Okay.
And that's a measured number. It's not exact. And the molality is only 2. So what's the freezing point then?
0.60. No, negative 0.60.
The freezing point then is going to be negative 0.60 degrees Celsius. Because pure water freezes at 0. Any questions? Strong electrolytes also affect the vapor pressure. And when we're doing vapor pressure calculations, we have to think about the dissociation of the solute when we're calculating the mole fraction. Okay, a solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. And they're giving us the vapor pressure of the solution and the vapor pressure of pure water, and asking us to calculate the number of moles of sodium chloride in the solution. This is one of those problems you have to think about. You can't just pull out an equation and plug stuff into it. Well, the vapor pressure. So the pressure of the solution, the vapor pressure of the solution was equal to what? You remember? Another funky capital Greek letter. Chi, the mole fraction of the solvent times the vapor pressure of the pure solvent. It's a good thing that test is open book, huh? So we are given this, right? This is the vapor pressure of the solution. Do we need to use the temperature? No. We just need to know that this vapor pressure is measured at the same temperature as this one, because vapor pressure depends on the temperature. So as long as they're at the same temperature, it doesn't really matter what the temperature is. But this is P solvent. So we can calculate chi solvent, the mole fraction of the solvent. So let's do that. So the mole fraction of solvent is going to be the vapor pressure of the solution divided by the vapor pressure of the pure solvent. So we've got 25.7 torr divided by 31.8 torr. And we get 0.80818. What are the units on that? No units. It's a fraction, mole fraction. If you come up with a mole fraction that's greater than 1, you did something wrong. Okay, just like a percentage, you think of a kindergarten class. Could we have 150% of the class be boys?
Unless you have visitors.
Well, but even if you had visitors, I mean, it's still out of the number of students, right? So 150% would mean that out of 100 people, 150 of them are male. Doesn't make any sense, right? Mole fraction can't be larger than 1 either. So this is the mole fraction of the solvent. So what does that equal? Mole fraction of, I'm going to start calling it water because I'm tired of writing the word solvent, because water is the solvent here. The mole fraction of water then is the moles of water divided by the moles of water plus the moles of what? The solute. Well, they gave us the moles of water, and we just calculated the mole fraction, so we should be able to calculate the moles of solute, right? This ends up being a little bit of an icky math problem. So there's a little bit of algebra here, and I'm going to skip some of it. I hope that doesn't bother anybody. I think I did that right.
You need X, the chi H2O.
Oh, I need a chi H2O there. What did I do? That's supposed to be chi. Because what I did is I took this and brought it down here, and I put that up here. And then I subtracted this from this side. So I think that's right. So this is the moles of water, 0.115, divided by the mole fraction, and then subtracting the moles of water. So 0.115 divided by 0.80818 equals, and then subtract 0.115. So I'm getting 0.027 moles. Okay, so there's moles. The solution, remember we're talking about ionic compounds, we're talking about electrolytes, and this is sodium chloride. When sodium chloride dissolves in the water, what does it do? It separates into ions. It's the number of particles of the solute that are important. So here, I purposely did not call that NaCl. This is the moles of moles of solute particles. I was get choked up about that. Moles of solute particles. So what are the solute particles? It's the sodium ions and the chloride ions, right? So this is moles of ions. The question, though, is asking us for moles of sodium chloride. Well, if I have that many ions, do I have twice as many moles of sodium chloride or half? It's half, but we have to stop and think about that, right? You can do a conversion factor and say, well, moles of sodium chloride is what I want, and moles of ions is what I've got. So sodium chloride, 1 mole of sodium chloride makes how many moles of ions? 2. If you were being rigorous, you'd go look up the Van 't Hoff factor and you put 1.9 in there, but we don't care that much about this one. So then I'm going to take that 0.0273 and divide it by 2. And that means that the solution was 0.01. I rounded that other one, so I better round this one too. Divide by 2.
And where did you get 1 mole of NaCl per 2 mole of ions?
From the formula itself. So when I look at this formula, NaCl, when that ionizes, it forms 2 ions. 1 unit forms 2 ions. So 1 mole of sodium chloride forms 2 moles of ions. Okay. So there would be about 0.014 moles of sodium chloride.
So the more complex the molecule, the more complex that last part's going to be.
Right. Like if you had iron 3 chloride, FeCl3, and you weren't given the Van 't Hoff factor, then you would just look at that and say, well, I have to assume that it's all going to dissociate. I'm going to get 3 chloride ions and 1 iron ion, and so then you'd have a 4 down here. Okay?
Gotcha.
Any questions?
That would always
Glucose is easy. It doesn't ionize.
Ah,
Yeah.
never mind.
Question in the back.
I was saying, like, that's all we can give to us there, right?
The Van 't Hoff factor would have to be given to you. You don't need to memorize that. Osmotic pressure has a lot of applications in medicine. Here's some micrographs of red blood cells. Here we've got normal ones. They're kind of donut shaped. These are shriveled up, and these are swollen. And if these continue to swell, they'll actually burst. And that would not be good if that's happening inside your veins and vessels. Hyperosmotic. Hyper means more. So hyperosmotic, also called hypertonic, are going to have, these solutions are going to have a greater osmotic pressure than bodily fluids. And so what they do is they draw the liquid out. So a very salty solution is going to draw the liquid out. And what that does to the blood cells is called crenation. I don't think this is on your final. I know it always shows up on the 3A final. It's not really very nice. Crenation is a word that's like just barely mentioned in their book. And then it shows up on the ACX final. Crenation is what's happening with these blood cells. The water is being pulled out of them, and so they shrivel up. Not a good situation. Hypoosmotic or hypotonic is where the solution has a lower concentration of solutes than what's inside the cell or on the other side of the membrane. And so then the water goes into the cell, and it causes the cells to swell up. And if they continue to swell, they'll burst, because that osmotic pressure can build up pretty significantly, enough to burst cells. Any questions about that? For human bodily fluids, an isotonic solution, iso meaning is a prefix meaning the same. An isotonic solution will neither draw liquid out of your cells nor cause it to go in. It'll just be kind of neutral. And so 0.9 grams of sodium chloride per 100 milliliters of solution. That's a mass to volume ratio, or it's also called 0.9% mass to volume. So 0.9 grams of sodium chloride in 100 milliliters of water or solution. And so we see a lot of percent units in medicine because they're easy to make up. They're easy to make the solution. And they're not concerned with chemical reactions occurring and how many moles there are. And so they use convenient units like percent mass to volume and mass of solute per volume of solution.